Hi, I would like to start by thanking Dr. Camilla and Dr. Hori for making me the honor to speak at this conference. I'm extremely happy to have this opportunity. So, I'm going to talk about neuroimaging and artificial intelligence. What do we need? What is out there? And how can we do better? So first of all, let's talk about some of the issues in neuroimaging research that require attention. Neuroimaging data require a lot of processing, such as denoising, artifact correction, image registration, image segmentation, and typically the end goal of all those processing is to improve diagnosis of certain pathologies. For the past 3 decades, researchers have relied on traditional computer vision and machine learning methods, but many of these methods are still far from being perfect, and also they don't generalize well. Not surprisingly, deep learning has become increasingly popular in the medical imaging field over the past few years. It is used in processing pipeline for tasks such as segmentation of healthy and pathological tissue structures and categorization tasks for the purpose of diagnosis. In fact, deep learning is taking on very rapidly in the medical image community. And as an illustration, the main MRI conference has seen an exponential increase of abstract submission related to deep learning for the past few years. So in today's talk, I would like to discuss the following 4 themes. First concerns the issue of generalization. The second one will address continuous learning in the context of medical imaging. And lastly, we'll review some of the recent initiatives of the AI neuroimaging community for sharing data and for sharing code. So let's start talking about generalization. A strong limitation in AI in medical application is that usually few data are publicly available due to privacy reasons. Moreover, creating manual labels to train models is extremely time-consuming, and this task is usually done by explorators such as neuroradiologists, and that time is extremely limited and costly. Another problem is that when a model is trained and validated on a particular dataset from a hospital, here on a T1 weighted contrast, usually does not work as well when applied to datasets from other hospitals or other contrasts, which might use different parameters, different vendors, different scanners. Here is an example of a T2 weighted contrast where the model failed to detect this lesion. Another thing also is that when you see a lot of publications, models are usually trained on beautiful and well-curated data. But real-life radiology data are hampered by motion artifacts, different patient morphology, and so on and so forth. To give you an example, here are sagittal MRIs across various individuals. The model can easily learn to perform tasks on this single data domain. However, in real life, data can be acquired with different sequences, parameters, manufacturer, field strength, etc. And the variability can be huge. And there are a lot of medical imaging challenges out there, like on Kaggle, for example. But in most cases, the data are constrained within one specific domain. So I feel that a lot of effort is spent by medical AI researchers to gain just a few dice score on segmentation challenges, but we are really missing the big picture here. How can we make these models usable by clinicians today? And I think that this is the most important issue that needs to be addressed as soon as possible. So what are the possible avenues? There are generative adversarial networks, or GANs. They can be used to generate a synthetic domain, and each new domain would then be mapped to this synthetic domain to perform a task. However, there are certain problems associated with GANs, even though they have become very popular. One of the problems is that image features not only vary between centers, but also across parameters. So it's difficult to find domain that would work for the infinity of parameters that we can get with MRIs. Another problem, more sneaky, is that domain adaptation can introduce bias, and you can find more details on the work by Joseph Paul Cohen. Another thing that we should absolutely consider is the multi-contrast approach. Within a typical MR session, several contrasts are acquired. For example, a T1 weighted, T2 weighted scan. And when radiologists look at images, they always have multiple contrasts opened in parallel. So they do a joint analysis, taking into account all the available contrasts. And that's very useful because one contrast can have an artifact, for example, patient motion or Gibbs artifact, and looking at other contrasts can rule out these artifacts. The problem, however, is that if we create a model that works for 3 specific contrasts, then during the inference, we need those 3 contrasts. Some work has been done, notably at Mila, to deal with missing contrasts. The HEMIS framework is an example that we've worked for the past couple of years in my lab. Lastly, another really cool approach that I'm very interested in is to add priors from MR physics information to generalize models better. We know that some parameters, such as the transverse relaxation time, or T2, flip angle, T1, echo time, B-naught field, bandwidth, repetition time, all contribute to the image contrast. So why not introducing them in the model training so the model would learn how these parameters affect the image contrast? So this is something we're currently working on, and I'll show you some preliminary results. First, we looked at the film architecture. Film stands for Visual Reasoning with General Conditioning Layer. And in other words, it learns to adaptively influence the output of a neural network by applying an affine transformation to the network's intermediate features based on some input. In the original film, it was demonstrated for visual and language tasks, but let's see how we can adapt it for an image segmentation task. So let's take an input image, a typical convolutional neural network, or CNN, which outputs a segmentation. Okay, so there's nothing miraculous so far. But then we can adapt this CNN to the film approach. And some of the outputs of some layers is modified by an affine transformation, you can see here, defined by the parameters beta and gamma. These parameters depend on what we call the film generator, which is a multi-layer perceptron that takes as input MRI parameters, such as flip angle, repetition time, etc. So during training, film learns to adapt its affine parameters based on the image and labels it sees. Okay. So our hypothesis here is that the film generator learns how the image contrast is generated by the various MRI acquisition parameters, and that would ultimately enable the model to generalize to unseen contrasts. So that was our hope. Unfortunately, our preliminary results were not so encouraging. For simple tasks, segmentation of large and consistent structures, such as the spinal cord on MRI data, a UNet trained on multiple contrasts gave similar results as the filmed architecture. For more difficult tasks, such as MS lesion segmentation, which is highly imbalanced, the highest achievable dice was around 0.7, and we realized that it was actually caused by a very large inter-rater variability. So that was the bottleneck of all our experiments, inter-rater variability. We did further work on that, but I'm not going to talk about this now. Let's go back to the film. We tried to simplify the experiment. Instead of inputting in the film generator MRI acquisition parameters, which are defined on a continuous range, The TR is basically a float number, similar for the flip angle TE. So there is just too much degree of freedom. So our alternative approach was to input categories. And our test bench was a spinal tumor dataset from a collaborator in Beijing, Dr. Yao Liu. And this dataset consists of 343 patients with 3 different types of tumor. Each tumor type has a very distinctive signature on the MRI in terms of signal intensity, size, presence of edema, and cavity. To accommodate a very large variety of image sizes, the first step consisted in localizing the spinal cord with a 3D unit. So this is a very robust first step. And the second step consists in segmenting the spinal tumor, edema, and cavity on images with 2 different contrasts. So it's a multi-channel input and a three-class model. And results showed a higher performance for the filmed unit versus the regular unit, meaning without prior information about the tumor type. So you can find more details about validation in the middle article, as well as in the Neuroimage clinical article that was just published. Last but not least, an important contribution of Andrea Lemay's project is that she made the model available on the Spinal Cord Toolbox, which is an MRI analysis software widely used by the community, which is developed by our lab. So this model is currently available and being used by several collaborators. Feel free to use it and give us feedback. So we talked about the issue of generalization and avenues to incorporate prior knowledge to improve the performance of deep learning models. The next point I would like to address concerns continuous learning in medical imaging. Like other image databases, such as dogs, cats, cars, planes, medical image databases in hospitals are rarely frozen in time. As images from new patients are acquired, it would be desirable that these images, along with the expert rating, actual diagnosis, treatment outcome, image segmentation, all those would be used to fine-tune the existing deep learning models or to create new tasks. Moreover, the issue of deep learning generalization that we talked about earlier can partly be addressed by aggregating data from multiple hospitals so that models would be exposed to a wider heterogeneity of image characteristics and patient population. Continuous learning is therefore a very attractive strategy in radiology. However, its implementation is far from being trivial. One of the biggest challenges concerns the sharing of medical data, especially in the context of international collaborations, due to various legal, privacy, and data ownership challenges. Strategies to partially overcome the issue include federated learning, where model training occurs locally at each participating institution, and only model characteristics, such as parameters, gradient, weights, are transferred to the aggregation server. So we don't transfer the data, we only transfer model characteristics. Another well-known problem in continuous learning scenario where early data would not be available anymore is that the injection of new out-of-distribution data could degrade the overall performance of the model when it's applied to earlier data. So this is called catastrophic forgetting, and it could be mitigated by careful quality control of the generated model over time. Also, current research that looks at regularization method to mitigate this issue. Finally, a very practical but real issue is how to implement a continuous learning solution across the different clinical sites. Challenges include implementing the software ecosystem and secure connections between participating sites, dealing with local ethics committees, training the personnel to use the data sharing technologies, standardizing procedures, acquisition protocol, experts labeling, and doing the quality control and the curation of the datasets. The list is longer than that. So this last point about data curation is an extremely important aspect, which actually goes beyond medical data. So I would like to address this in the last part of my talk, data sharing practices. How can we do better? Let me give you an example. Imagine that one of your collaborators asks you to train a model that does brain tumor segmentation. They send you a data set of hundreds of subjects. Problem is, the data set looks like this. At the end, instead of spending time finding the best deep learning architecture and optimizing hyperparameters, which is exciting, your entire PhD will be spent curating the dataset, organizing and renaming the files. And you will end up like this guy. Obviously, sharing such datasets should be avoided because it leads to wasted time, lack of reproducibility, and it makes it difficult to scale a training strategy that combines multiple datasets. And as I speak, many datasets that look like this one are being shared by the scientific community. So this practice really has to change. How can we make it change? A few years ago, a group of neuroimagers at Stanford came up with a convention for structuring and naming neuroimaging files. The standard is called BIDS, for Brain Imaging Data Structure. In the early days, it was dedicated to brain functional MR datasets, but given its rapid and wide adoption, it extended to non-brain regions, such as the spinal cord and other modalities, including CT, PET, EEG, MEG, and microscopy. There are actively maintained converters to get your raw data into BIDS structure, and there are validators to ensure BIDS compliance. Another cool feature is that there is a convention for data deriving from raw datasets, such as expert labels or segmentation. And also each image has its associated metadata file that includes acquisition parameters. And those could be extremely useful for injecting relevant information during the training of deep learning models, as we saw earlier with the film approach. Last but not least, the neuroimaging community has been putting together repositories that are free to use for everyone who would like to share a BIDS dataset. So this standardization initiative also comes with an increasing amount of shared and curated dataset, which is great. Now, what would be really cool is if there was a software ecosystem that would be compatible with BIDS dataset. Fortunately, there is one. I'll do a bit of self-promotion here and introduce EvaDome, which is a software project we've been working on for the past 3 years in collaboration with folks at Mila. EvaDome is funded by EvaDo, that's where the name comes from, and it's an integrated framework for medical image analysis with deep learning based on PyTorch. Some of the features of EvaDome includes the possibility to dump any BIDS compatible dataset without the need to do any manual curation. EvaDome also includes bleeding edge techniques and architectures, many of which have been created at Mila. And we also included few tutorials to make it easier to dive into the ecosystem. Like any open source project, we welcome feedback, contributions, so please download it and try it. So putting this all together, our lab is involved in a couple of multi-center studies where we aim at translating all the things I showed you earlier to the clinical setup. One concrete example is a pan-Canadian project named CANPROCO, led by neurologist Dr. Ho at St. Michael's Hospital in Toronto, and it involves nearly 50 researchers across Canada. So multiple sites will gather data and store them into their local server. We're talking 1,000 participants here. These raw data are continuously sent to a centralized server, or TBC, and there they are QC'd and converted to BIDS. BIDS datasets are sent to an AI node located in my lab in Montreal using SSH protocol and Git Annex technology to version and track the data. There, the existing model is updated with transfer learning and continuous learning scenario, and QC to make sure it does not derive too much from the existing model. And then the new model is sent back to the UBC server, which redistributed to all the clinical sites where the inference can be performed. This inference could be MS lesion segmentation, and then it is disseminated to the radiology department and researchers via the internal PACS system. So what I presented you here is the big picture. There is, of course, a lot of detail that needs to be figured out. We're still looking into how to implement this framework in the large scale, especially on the continuous learning part. So if anybody is interested in chipping in, helping in, please shoot me an email. We are open to collaborations. So let's conclude this talk, starting with the question, what can AI do for neuroimaging research? The short answer is a lot. Today, we mostly talked about segmentation and labeling tasks, but AI also has strong future in categorization tasks for diagnosis and prognosis. What do we need? What is out there? The take-home message here is that I think we should focus on strategies to generalize models across various data domains. And an open question is, how can we incorporate priors from MR physics? We talked about a much needed continuous learning strategy for specialized medical data lakes, such as MS, spinal cord injury, and cancer. And we also discussed recent initiatives to improve sharing of neuroimaging data, one of them being the BEADS initiative. Of course, we can do better. And in fact, I haven't talked about one critical aspect of neuroimaging, which concerns the pre-processing of images. Images coming out of the scanner need to be filtered, corrected for artifacts, realigned to a template, etc. When we look at some of the machine learning medical challenges, such as the BRATS for brain tumor segmentation, images are already pre-processed. So people can focus on optimizing the deep learning part. But what's really frustrating is that when we take the winning architecture from the best Kaggle challenge, it cannot easily be put into practice because the performance of the model will strongly depend on the pre-processing pipeline. And there is a lot of work to do in this area as well. I think the neuroimaging/AI community doesn't talk enough about this boring aspect of pre-processing, which is why I call them the hidden step. Another promising avenue, along with the enrichment of data lakes, is the incorporation of multiple data types for further improvement of model prediction. So with that, I would like to thank all members of the Neuropoly Lab, the collaborators, and the funding sources. And thank you very much for your attention.